Hello and welcome to Lecture 2 of the Acceleration Unit in Phys 1104. We're going to start this lecture off with a few more general things about acceleration, and then the rest of the lecture will be spent on the special case of motion with constant acceleration. In the usual spirit of working from observations towards hypotheses that I've been using in these video lectures, it's time to grab some new data. So here is a cart, which I've pushed, and you can see that the track that it's on is slightly tilted. And so as it goes up the track, it is slowing down. You can see that a little bit from the points that the video editing software is putting into the motion diagram. And it eventually stops and turns around and heads back down, at which point it's speeding up. And I have defined axes for the video editing software to use so that the x-axis points parallel to the track and up the slope. So you might not like that idea of a slightly tilted axis system, but just think about it. That means that the cart is moving along the x-axis. And so we only have to worry about x components of positions, displacements, velocities, accelerations, and so on. And I've exported the data from the video editing software and brought it into a spreadsheet so that I can graph the data. And this time I had the video editing software calculate the x component of the velocities for me to save a bit of time. So I have both graphs already. Let's use what we've just learned about the signs of the components and look at the x versus t graph to figure out which way the acceleration vector is pointing for this cart during various parts of its motion. So first of all, notice there's this part up here where the slope of the graph is 0. So that's when the cart is momentarily at rest and it's turning around. So everything before that, it's going up the ramp, and Vx is positive with our choice of axes, and everything after that, it's going back down the ramp, and Vx is negative. Now, because this is accelerated motion, the x versus t graph isn't a straight line. The curvature of it is telling us about the acceleration. Here, at 0.5 seconds, the slope of this line should be the x component of the velocity. That's an approximation of the tangent line. If you look a little later on, you see this slope. It's less steep. And so throughout that region, Vx is decreasing, and that tells us that Ax is negative. Now let's look after it turns around. At 2.5 seconds, the slope of that line should be Vx. And at about 4, the slope of that line is Vx. So notice it's getting steeper, but it's a negative slope. And so that means the slope is getting more negative. And so again, Ax is negative. So whether we're talking about when it's going up the ramp or when we're talking about when it's going down the ramp, the acceleration vector points back down the ramp in the negative x direction the whole time. We'll continue to gain more insights by drawing graphs, and so let's draw the Vx versus t graph. We already know that at this time, indicated by the dotted gray line, Vx is 0 because the slope of the x versus t graph is 0 there. And we know that the slope is positive everywhere here, and so Vx is positive everywhere over here, and similarly Vx is negative everywhere over here. And we already know that it's decreasing through this whole time. But beyond that, just by looking at the graph, the x versus t graph, we can't tell the shape. It could be something like this, or it could be something like this. Both of those are decreasing everywhere. So now it's time to actually calculate it, and we'll use the definition that we already know, where this is just a rise over a run, except as before, we're going to talk about smaller and smaller delta t's to get the instantaneous velocity, or as good an approximation of it as we can with the data we have. And when we do that, this is what we find. And it looks rather linear, which is perhaps a surprise. Now we're going to use our definition of acceleration, or the x component of the acceleration, to get the acceleration from our Vx versus t graph. So we see our average x component of acceleration is a delta Vx over delta t. And very similarly to what we did before, determining average velocity components, we can interpret this as a rise, delta Vx, on our graph, over a run, delta t, on our graph. And so this ax av can be thought of as a slope on our Vx versus t graph. So I've used the spreadsheet to do a line of best fit of the data, and it informs me that the slope is negative 0.32. And we should think about the units. Whenever you do something and the computer gives you a number, well, the spreadsheet isn't clever enough to tell you the units. You need to make sure you know what they are. Note that it's come from something that's a delta Vx, which on my graph is in meters per second, over a delta t, which is in seconds. And so I take meters per second divided by seconds, and I'm going to get units of meters per second squared. But that may have been what we expected as the units, but you should be careful. I might have been working in centimeters, and these Vx's might have been in centimeters per second.
Let's check your understanding. So here is a Vx versus t graph, and look at it and figure out which of these is the most correct Ax versus t graph.